So let's go beyond, into this glorious three-dimensional space that we all inhabit. So let's say we want to store objects in 3D space because we want to simulate, say, planets orbiting in real space, or we want to make some video game where things are in space and we want to be able to find nearest neighbors for, I don't know, some kind of collision detection type problem. Who knows? So we can't use quad trees for that because they only have 4 directions. But in 3 dimensions there are 8. That is, there's forward and to the left and up, there's forward to the right and up, back and to the left and up, back and to the right and up, and then all of those but the down versions. So one approach is to use an octree. I've seen it spelled both ways, and it's basically just what you'd expect. It's like a quad tree, but you have 8 neighbors, one corresponding to all those 8 dimensions or directions. And so this is the random diagram I grabbed from online, basically showing that you start from a space, you break it into 8 subspaces, each of those can be broken into 8 more, though of course in an octree there's some really nice diagrams, if you go looking, like this bunny thing here, showing that in a region where you're far away from any points, it's partitioned very coarsely, but where there is stuff, it's partitioned very finely. And it's just really beautiful, these kind of images you get out of these. Though I'm not going to talk too much about them, because they're just the natural generalization of quad trees. They're used very widely in practice, and if you go off and take some kind of computational, what was I going to say? Computational what? Geometry? I guess so, yeah, computational geometry, computer graphics type class, you'll likely run into an octree somewhere. But I don't want to talk about octrees because, again, they're just not that different than a quad tree, so we're going to go crazy, and we're going to go into just arbitrary dimension data and say, let's go beyond 3D. So could you make something with 16 neighbors or whatever else? Like, keep stepping that up? Yes, but it's going to get real ugly real fast. So we're going to talk about something else known as the KdTree, which handles arbitrary numbers of dimensions. And as a motivating example, you may ask yourself, like, why would I want to do this? Is this some kind of like crazy science fiction simulator? I want to somehow capture the idea of 80-dimensional space? Well, often dimensions aren't space at all. They're just properties of objects. So let's say we have some database of a bunch of songs, and we want to find songs that are between 3 and 6 minutes. That's the length dimension. And we want it to be between 1,000 and 20,000 listens. Well, that's the popularity dimension. And we want it to be between 120 and 150 beats per minute. That's the speed dimension. And then lastly, we say we want the when it was recorded dimension, what era it's from. And maybe we want it to be after 2004. Well, one approach you could take is store all of your music data in a big KdTree, and then do some kind of, this is basically just a rectangle query, but now in 4 dimensions instead of 2. Now, if you take a databases class like 186, you'll talk about how this is really done, but a KdTree is one way you could do it. So it's a really neat data structure that I like a lot, KdTrees, because it's a cute idea. It's like, so, as you'll see, it's so simple and it generalizes really well, and it's kind of amazing that it works. Now, for the sake of being able to visualize and see this as a demo, I'm actually just going to do it in 2 dimensions. So that is, it's going to be a KdTree where k is an arbitrary number, but I'm going to pick k equals 2 because then we can see what's happening. Now, I'm actually not depriving you of anything because the idea generalizes so nicely to higher dimensions without any thinking. So without further ado, the KdTree, basically how it works is in 2 dimensions, the root is going to partition the entire space into a left and a right side, so by x, and then all depth 1 nodes, that is a's children, will partition by y. And then all depth 2 nodes, well, they're going to partition by x, and we'll just alternate x, y, x, y, x, y. And in 3D it would be xyz, xyz, xyz. In 4D it would be wxyz, wxyz, wxyz. And interestingly, it does actually work pretty well, even as you increase the number of dimensions up to a certain point. So let's see an example of how this would be built, and that'll make this diagram more clear. Okay. So we start with an empty KdTree, and we try to insert a, which is, that is, we want to associate the 0.23 with the value a. So that's at this point in space, and I'm going to represent these nodes a little different looking than we did with the quad tree. I'm going to show them explicitly with a letter and a point over here. Okay? So you can think of this as the key, and this is the value. So on the left, I'm showing the KdTree, and on the right, I'm showing you where they are in space along with the partitioning. Okay? So at this point, we're actually basically just where we were when we said, let's just build a binary search tree where we only use the x value. But where it gets interesting is that if I insert, say, z with value 4, 2, well, we would compare the x coordinate to this 2. And we'd say, well, 4 is bigger than 2, so we'll stick it off to the right. Okay? Now at this point, because z is at depth 1, we're going to think of it as partitioning the space into the top and bottom. Okay? So here only the 2 matters in terms of the ordering. Right? The reason that z ended up to the right of a is because that this value here, 4, it was greater than 2. All right, now comes along insert 4, 2. So now I'm trying to associate the key 4, 2 with b. And here I'm assuming this is a map. So all that's going to happen is that since 4, 2 is already a key in our KdTree, then we're going to replace it with a new value. Okay, so z becomes b. So just a reminder that this is basically just a map. Okay. Alrighty, so next comes c. So c, it has x coordinate 4 and y coordinate 5. So we would compare the 4 to the 2 and say that's bigger. So we go to the right. And then we would compare the 5 to the 2 in node B. And since 5 is bigger than 2, we end up here. Okay. So what's interesting, you'll note, is that we compared our 4 to the x-coordinate of A and our 5 to the y-coordinate of B. And since this is a depth 2 node, we're going to think of it as splitting the space into a left half and a right half. So only this 4 will matter from now on. Next up comes inserting 3, 3. So maybe pause the video and think about what's going to happen. Now let's give you a hint, which is that we're going to start by comparing 3 to the red 2 in the root node. Okay, so we compare 3 to the red in the root node. Then we compare 3 to this blue. It's bigger, so we go up. Then we do 3, and we say 3 is less than 4. So D is going to end up right here. Okay. So we went to the right of A, to the up of B, to the left of C, and ended up in this position. Alrighty. Another point. Our last one, 1, 5. So let's say we insert 1, 5 in this case. Again, maybe pause the video. But what will happen is since, oh wait, I think there's, is that it? Maybe there's 2 more points. I don't remember actually. So anyway, we're going to insert E, which is 1, 5. And what will happen is that, yeah, there's 2 more points. There's E and F. Oh my goodness. Anyway, so we're going to insert E, which is 1, 5. And since 1 is less than 2, we just end up here. That's an easy one. Okay. And then lastly, we have point F. 4, 4, which is F. So in this case, there's one little detail I need to give you if you want to try and do it without me spoiling it, which is that if we have a tie, then we are going to treat it as greater than. Okay. So given that ties are broken by greater than, what happens? So here, we compare 4 to 2. We compare 4 to the blue 2. We compare 4 to the red 4. And at that point, since it is a tie, we will go to the right. So we're going to treat equal items as greater, because we only have a left and a right child. So we have to do something. Okay. Now the reason that's not a problem in a normal binary search tree is that if you're equal, you just replace the key, or sorry, you would just replace the value with the value you're trying to add, right? So if you put something with the key value that already exists, you replace it. But here, we're only doing one comparison. So it wouldn't make sense to replace C with F because it's not the same key, right? This is 4, 5 versus 4, 4. So we have to break ties in a KdTree, and we do it by just arbitrarily breaking ties in a consistent way. In this case, I'll treat it as larger. All right. So at that point, we've built a KdTree, and we see here that we have nicely partitioned the space in a different way than we had with the quad tree. And so we'll pick this apart in a little more detail in the next video, but there you have it. That's a quad tree. That's a KdTree. And if it didn't totally make sense, try building it yourself from scratch, and you can do so by stepping through this video another time.